The term TCP global synchronization almost sounds like a good thing, maybe even the name of a cool techno band. But as we'll see here shortly, it's neither one of those. Global synchronization occurs when a large number of TCP connections experience packet loss simultaneously. This could be due to a momentary connection problem somewhere in the network, but more commonly it's simply due to a surge in traffic filling up the buffers on a router and getting tail dropped. To understand global synchronization, we need to understand the life of a TCP connection. When two TCP hosts establish a connection, they don't just immediately begin sending data as fast as possible. Instead, when a TCP connection is initially established, each host will send only a small amount of data that is typically going to be the same size as the TCP maximum segment size, or MSS. The MSS is simply the maximum amount of data that can be crammed into a single TCP packet. Generally, the MSS is going to be the MTU, the maximum transmission unit, minus the size of the TCP IP header. On Ethernet, the MTU is generally 1500 bytes, and the TCP IPv4 headers are 40 bytes. So a common TCP MSS is 1460 bytes. Now let's say that hosts A and B have just set up a TCP connection, and host A has something to send to host B. Host A is going to send one TCP packet, and then it's going to wait for host B to acknowledge it. When host B acknowledges that first packet, host A is then going to send two packets before waiting for an acknowledgement. Once host B sends back the acknowledgement, host A is then going to send 4 packets to host B, and then when host B acknowledges the next packet, host A will send 8 packets at a time, and then 16, and then 32, and then 64, and you get the idea. This behavior is called TCP slow start, which ironically is actually designed to prevent slow starts. It's also called TCP ramp up because the sender continually increases the rate at which it sends packets. Now, at some point, TCP is going to hit some sort of ceiling and it won't be able to ramp up anymore. Eventually, it will utilize all the available bandwidth and it will begin to experience timeouts or packet loss. When that happens, the sender will drop back to sending one packet before stopping and waiting for an acknowledgement, and the cycle repeats. When you look at this on a graph, you can see that this behavior creates a characteristic sawtooth pattern, an increase followed by a sudden drop. In a normal IP network carrying TCP traffic between multiple hosts, this pattern is going to be offset for each host. In other words, they're not in any way synchronized. But suppose that a major link in the network becomes saturated and causes all of those TCP connections to start dropping packets. In response to the congestion, all TCP senders will simultaneously go into slow start. They will slow down the rate at which they send, relieving the congestion. Once the congestion has abated, they will begin sending again and will continue to send packets faster and faster until congestion occurs again. And they'll all ramp up at the same time. And guess what? They'll use up all the bandwidth available and start dropping packets again. And then what happens? That's right, they'll all stop sending packets, go back into slow start, and the process repeats. This is called TCP global synchronization because all of the TCP connections become synchronized. This is a problem because, as you can see from looking at the graph, the full bandwidth is not getting utilized except for a very short time at the peaks just before everything drops. By the way, what is the solution to this? Well, frankly, it's to make sure you have enough bandwidth. If that's not possible, then you'll have to implement a quality of service tool such as shaping or queuing.